Cells are complicated. If you are interested in observing an individual feature or process in a cell at high resolution, such as how the cell is adhered to some substrate, or how an individual vesicle enters or exits the cell, you may find that traditional microscopy techniques that illuminate large portions of the cell just produce too much noise. In such cases, specialized techniques in microscopy that limit your field of observation can be very valuable. One such technique is turf microscopy. TIRF stands for Total Internal Reflection Fluorescence. To understand why TIRF microscopy is so powerful, we first have to understand the phenomenon of total internal reflection and its consequences. Suppose we have a beam of light traveling from a medium of higher refractive index to one of lower refractive index, such as glass to air. The angle at which this beam refracts is described by Snell's law, Ni sine theta I equals Nt sine theta t, where I and t stand for incident and transmitted. Because we are going from high to low refractive indices, at some incident angle, the transmitted beam will be parallel to the interface. We call this the critical angle, theta c. At incident angles greater than this critical angle, the beam is said to be totally internally reflected. Even though we just said the beam is totally internally reflected, let's try and describe the transmitted part of this beam mathematically, as a simple solution to the wave equation in 2 dimensions. First, let's take a look at the y component, e to the ik sine theta ty. We are dealing with an incident angle above the critical angle, which we defined earlier as the inverse sine of nt over ni. We can also rearrange Snell's law to get the incident angle in terms of the refractive indices and the transmitted angle. A little simplification reveals that this implies sine theta t is greater than 1. Huh. Well, that's a little weird. What matters for our purposes, though, is that this means sine theta t is real and it's positive. Going back to our wave equation, this means that there is still something being transmitted in the positive y direction, even under total internal reflection. Now let's look at this x component. Rearranging everyone's favorite trig identity, sine squared theta plus cosine squared theta equals 1, we can see that since sine theta t is greater than 1, cosine theta t is actually imaginary. Let's call k cosine theta t id, some fully imaginary number. Plugging this back into our wave equation, we get a decaying exponential term. This shows that whatever it is that is being transmitted in the positive y direction does not propagate like normal electromagnetic radiation, but rather decays to near zero intensity after just a few wavelengths. We call this an evanescent wave. Okay, enough math. Let's apply this to microscopy. Using total internal reflection, we can transmit an evanescent wave into our sample which quickly decays, only interacting with the portions of the sample very near the interface. This technique was first theorized to have a biophysical application by E.J. Ambrose of the UK's Institute of Cancer Research in 1956. Ambrose was interested in studying the points of contact between cells and a substrate to better understand the phenomena of contact guidance and contact inhibition, both of which are important to understanding the growth of cancers. His proposed apparatus had some limitations, however, and did not yet involve fluorescence, so is a form of TIR microscopy. Modern turf microscopes improve on this design by sending the beam causing the evanescent wave through the microscope objective itself. Fluorophores are bound to the point of interest on the cell's surface and made to fluoresce by the evanescent waves, while fluorophores elsewhere in the cell and naturally fluorescent parts of the cell are unaffected. This results in a clear signal from your point of interest while drastically reducing noise from the rest of the cell. In the realm of biophysics, turf microscopy is particularly well suited to studying membranes and processes related to membranes. This includes studying the bilayer and proteins involved in the membrane itself, vesicles entering and exiting the cell, interactions between cells, and many other applications. Beyond the observation of cells, turf has a wide array of uses for single molecule detection and can be combined with other single molecule and super resolution microscopy techniques.